Okay, so we are live. Good morning, everyone. Today we are pleased to have Robin Kaiser as a speaker of the seminar series of the Brazilian Physical Society in the area of atomic and molecular physics. Robin Kaiser is a CNRS Director of Research at the University of Nice, Sophie Antipolis in France. He obtained his PhD at the École Normale Supérieure in Paris in 1990. Spending afterwards 1 year at Harvard University before joining CNRS in 1991. A few years later, he moved to Nice, where he is now leading a Photon-Atom group. He has published more than 100 papers on experimental and theoretical aspects of light scatter in cold atoms. His specialty is in light matter interactions, so to investigate cooperative scattering and understood localization of light, fluctuation and correlations of light in atomic systems and in stars, nonlinear optics, and in particular superfluidity of light and self-organization. In 2019, he received the prestigious ERC Advanced Grant of the European Union, and a few years before the Shell Prize from the French Academy of Sciences for his pioneering experiments on light propagation in random media of atoms. Since 2011, Robin is a fellow of the American Physical Society for fundamental investigation of multiple scattering of light in atomic vapors. The title of today's colloquium is Collective Atom-Photon Interactions. YouTube attendees can interact with the speaker by asking questions via chat that will be read by the committee members at the end. So please, Robin, you can start.
Okay.
Thank you very much.
Thank you, Tommaso, for this kind introduction. I'm really happy to be invited to this Brazilian community to speak about our work here in France. I put up my Natal T-shirt for this. As you can see in the next slide, where I will introduce my collaborators, which is very important, we have an extremely strong Brazilian connection here. So first, the most important people in my group are Mathilde, William, and Guillaume, who really run the day-to-day experiments and who are the people who have the memory of what happened in the last 10 or 20 years. This is extremely important for the experiments we do, and I'm more or less the commercial salesman who go around and speak on the things. But these three people are really the hardcore of our research, so it's really important to stress, and you should invite them as much as possible as well. Then we have a group of PhD students and postdocs working on the experiments I will present now. We have a very strong network of collaborations, which is very important. First, for me, collaborations are important because first you meet people from different countries, which is very enriching personally. And also you have to explain your ideas and you get new ideas from other people. And this list here is not just people I met on conferences, these are people with whom I share papers. So it's really just showing that this collaboration for me is at the heart of the way how to do research. And in bold here are the people who are from Brazil. So right now we have one PhD student on my ERZ project. Michel just left from Brazil. We have two postdocs from Brazil. We have a lot of collaborations, including Tommaso from Brazil. So it's clearly a very, very strong connection, and I hope that this French-Brazilian connection can be established in a more formal way for more groups to come. Okay, but now let's switch to science. So what we are really focusing on is collective effects. So our specialty is basically to trap cold atoms, but many cold atoms. So this is our main working horse. So it's a cloud of cold atoms. Let me just switch again to the pointer here. So this red blob here is like a few millimeter thick cloud of cold atoms, and we can trap up to 10 to the 11 atoms. So this is one among the biggest cold traps you can find. And as Phil Anderson said, if you have more, you get different things. More is different. You get not only enhanced features, but you get new emerging features coming out of larger samples or more complex behavior. So we study basically what we want to study is what is happening new or differently because you have so large cloud of cold atoms. And I focus in this talk on our effort towards Anderson localization, and on the path we stumbled about Decay Sub and Sub Radians. We also see pattern formation, which is a little bit like magnetism, which can appear in this cloud. We have kind of plasma physics, so this is a cloud of cold atoms in some regime where it becomes unstable. And we also did random lasing experiments with cold atoms. And starting from all this, we had to understand a little bit better what happened, and that's how we were led to study Levy Flight, and then now more recently quantum fluids of light. And we have one application of our technique, which is now going to astrophysics, and I will, at the end of the talk, hopefully have time to present you what we do in astrophysics. So we do a lot of things with, and all are connected to what happens if light interacts with many atoms. And so I will focus on three aspects: Decay and Anderson localization, Levy flights, and astrophysics. But of course, if you have other questions, we can discuss other things later on. Okay, so first, cooperative scattering of light. So the main goal here is Anderson localization of light in 3D. And this is kind of a summary of what can happen. So the idea is, what happens if you throw photons at a large cloud of scatterers? So in this picture in the middle here, you see fog. So if the light emitted from the top of the Eiffel Tower cannot go directly towards me, I see kind of a diffuse halo around the top of the Eiffel Tower. And this can be explained by just a random walk of photons, of particles. So there's no wave effect, which is really important to explain this picture here. But there are two other features where photons can be trapped in the system for a long time, which depend on interferences. And this is Decay Sub Radians and Anderson localization. And so the main picture you can have in mind is that Anderson localization, our main goal, is a photon which stays in a sub-region of this cloud here and will be trapped in this part here where I point here. And another photon will be trapped here. So that's the goal. We want to see if this is possible, and this will be called Anderson localization flight. Whereas Decay Sub and Sub Radians, Decay Sub Radians also would allow light to stay in the system for a long time, but the photons will be in an extended mode, so all over the cloud, not only in one part of the cloud. So the question is, these are different ways of keeping a photon in the system for a long time. Can we understand the different features? Are there phase transitions between these different mechanisms? Can we explore these mechanisms in a realistic system? And so we want to see if we can study these features in detail in our cloud of cold atoms. And Anderson localization of light is a very old story. It started in the 50s with mesoscopic ideas of electrons being trapped in disordered systems. And a lot of theory came around in the last decade. I just want to show here a scaling theory of localization, which was done in the 70s by the so-called Gang of Four. Here's the reference of this, which showed that in 1 and 2 dimensions, you would always have Anderson localization if you have a small amount of disorder, whereas in 3 dimensions, there will be a threshold for disorder. And all this is related to the probability of return. You know that in 1D, if you do random walk, you will always come back to the point where you started. In 2D, it might take an infinite time, but you also come back. But in 3D, depending on the parameters, you might never come back to home. So you will never get back home in 3D. So this return probability is making this aspect very depending on the dimension of your system. So this paper was very important because it showed that there is a kind of a universal approach to Anderson localization, and microscopic detail should not be important. But we have to be aware, and I come back to this later, that's why I started here, that there's no exact analytical theory of localization. There's approximated solutions like self-consistent theory of localization, and there are a lot of numerical simulations, but there's no exact theory of localization. And you see why I stress this here when I come back to our type of experiment. So people wanted to look for Anderson localization with different type of waves. My interest is of light, so electromagnetic waves. And the state of the art of as of today is that this has not been observed by any system. So the agreement in the community is that there have been 2 very important pioneering experiments by at Larendyk and by Georg Meret, by looking for this signatures of anisocation of light in 3D, but they could not see very clear signatures which could not be interpreted in different ways. So the state of the art is that there's no clear signatures of anisocation of light in 3D so far. So we want to take a different sample. People have studied semiconductor powders or white paint. So we want to change this sample by cold atoms and see if this helps. So to start this, we first need to do a benchmarking experiment. So we throw photons at our cloud of cold atoms, and we first have to start to study random walk, regular diffusion without interference effect. And this can be described by a diffusion coefficient, which is given by the square of the mean free path L here, divided by a typical time constant to do one step here. And the mean free path is given by the ratio 1 over the density of the scatters of the scattering cross section. So that's well known. So we can do this experiment with cold atoms very easily. So we take our cloud of cold atoms, come with the probe beam, and we look at how much light goes through. And if you have many atoms and if you are on resonance, no light goes through, and you can plot the total transmission here versus the optical thickness of the sample, and following Beer-Lambert's law, this coherent transmission in the forward direction will decrease exponentially. Then these photons, which will no longer go through, they will go somewhere. They are not absorbed in our sample. So they will be either scattered and go in the forward diffuse transmission regime or in the backward regime. And in the diffuse transmission, if you would have a slab, this would correspond to random walk crossing a slab of random scatterers. And this can be described by what is the equivalent of Ohm's law for photons. And the total light going through the sample would decrease like 1 over the sample length. So no longer exponentially, but like 1 over L. That's Ohm's law for photons, and we can easily measure this in our experiment. So far, so good. Nothing really new, just to show that we know what we do, and it's very important to do this in a very systematic way, not to be fooled by some other signature. Then what is also possible in cold atoms quite easily is to do time result experiments. So you come in with the pulse beam here, you switch on and off the laser beam, and because typical timescales in this cold atom are a few tens of nanoseconds, so nowadays it's easy to switch on and off lasers at this timescale. So we switch off the laser very quickly, and we look at how long the photons stay in the system. And if you look at this plot here, if you have few atoms, the photons will come out quickly. If you have more atoms, they stay in the system for a longer time. And from this late decay time here, tau 0, you can extract the diffusion coefficient here, which goes like the square of the mean free path divided by the transport time, or the transport mean free path times the transport velocity. And you can measure these things. And one a little bit surprising thing is that the transport velocity in our system is many orders of magnitude smaller than the speed of light in vacuum. There's no big surprise, so you could have thought that this small diffusion coefficient would be a signature of localization. It is not. This is just the fact that the atoms are very strong, have a very narrow resonance. It's like in a cavity, photons will stay in this resonance for a long time before going to the next resonance scattering atom. And so this is just a signature of a very narrow resonance in our atomic system. And there's no interference between different scattering paths involved here. So this is just to show you that measuring a small diffusion coefficient must be interpreted in very detailed manner before claiming any important results. Okay, so this was just random walk, no interference effect. So now we want to go towards underlocalization. So we want to probe interference effect. And there are two different regimes. One is called weak localization, which is easy to do. I will show you how this has been done. This has been done for many decades, but we also do it with our samples. And then the next important question is how to get strong localization of light. Okay, so weak localization of light is a consequence of the fact that photons are waves. So it's not just a random walk. There are interference effects here. So this diffusion coefficient here gets a correction term here, which goes like 1 over KL squared, where K is the wave vector, 2 pi over lambda, and L the mean free path as before. So you see, if KL is very large, so if the photons travel a long distance before changing their direction, then this correction term here is small. So in order to get a very strong correction due to this interference effect, you need KL to be of order of 1. And this is the hard challenge to do. That's very difficult to do. But if you can do this, then the prediction is that the diffusion coefficient would be 0, so light would no longer diffuse out, but will be trapped, and that would be called under-localization. And the corresponding criterion is the Interferometric criterion, which says that KL should be of the order of 1 to enter this regime. Okay, so how to do first this? So first to study this correction term, you go for a regime where KL is large and we get small corrections. So how to study small corrections? This goes under the name of current backscattering, and the situation is pictured here. So we take a random sample of scatterers. So you can take milk in glass and put water to dilute it, or you take cold atoms, very similar. You take a laser beam here, which fits this scatterer here, and then does a random walk, goes out to detector. There's another photon which does this pass here, it goes to detector. And of course, pass 1 and pass 2 will have interference terms, which will lead to speckles. But if I do a random configuration and I change the configuration of my scattering event scatterers here, then pass 1 and pass 2 will be uncorrelated. So the cross terms between pass 1 and pass 2 will be averaging away. But there will be one particular pass here, which is shown in dotted points here, which will go through the sample just in the reverse path as the full line here. And so this reverse path will, by construction, have the same path length in the sample in the forward and reverse path. So I have to be very careful before throwing away the interference terms between this direct and reciprocal path. So you can compute the path length difference, which is shown here. It still depends on the first and last position of the scatterers here. So it still depends on the position. But there's a prefactor here, K in plus K out, which is the instant wave vector and the detected wave vector. And you can see that if K in plus K out is 0, then this phase difference here is 0, whatever the position of the first and last scatterer is. So exactly in the backward direction, that's when K in plus K out is 0, there's always a constructive interference between this direct and reverse path. So I have in the backward direction always pairwise constructive interference, which leads to an intensity which is twice as large on average in the backward direction than in the other direction after averaging. So for optics people, this looks like a Sagnac interferometer here, which is well aligned without the need to tune any mirrors. And in a piece of paper for €1 or less, I have billions of this Sagnac interferometers which are self-aligned if I look in the right direction. So that's a little bit kind of a nice feature. So this is the expectation. So you get enhanced backscattering, and it's a signature of interference between multiple scattering paths. So we did this with our cold atoms. So to do this, you come in with a probe laser, you go on the cloud of cold atoms, look in the backward direction across the beam splitter, you put a camera in the focal plane of the lens, so every pixel on the camera corresponds to one scattering angle. And when you average many runs of this, many pictures of this, you get this type of peak here, which is enhanced backscattering in the backward direction. And this is a signature that you get a coherence and interference in multiple scattering, even though we drive the atoms on resonance. So this is a clear picture, a clear illustration that scattering of light by cold atoms is not a sequence of absorption followed by a random spontaneous emission where the phase is lost. Else I would not get this constructive coherent peak here. So you have to be careful when you picture scattering of light by atoms in a process that you first say absorption and then later on spontaneous emission. That can be very dangerous, and this is a case where this picture would fail. Sometimes the picture is very good, but this is a case where it would fail. Okay, so this is the experiment, very nice. We of course turn to a very detailed theory analysis, and we together with Dominique Delalande and Christian Manet-Miniatura, we developed the theory to adapt to this system here. And as I said, there's no exact theory, but there's something called a diagrammatic approach, which takes the intensity random walk and the reciprocal path, which is called Cooper terms. And then we did all the theory on this. And here on this plot here, you can see for different polarization channels, the comparison between the experiment and the theory. And there's no fit. This is just a simulation compared to the experiment. And this works so well that at that time, there was no reason to think that this diagrammatic approach would have any trouble at all. This was a really excellent agreement. So we really was full trust that this model would lead us fully towards the Anders localization regime. There were some problems to face. So first, I told you that you need to go for this high density regime where the Joffe-Regel criterion is KL of order of 1. This means L needs to be of the order of the wavelength. This means that the photon has to travel and hit another atom after 1 wavelength or less. So that's very difficult to do. So you need a very high density sample. People have done this. Mark Havey did this in his experiment. Antoine Brouwer has this. But no one has seen signals of Anders localization despite this high density limit. So there are other problems. And one of the possible problems is that the atoms used so far are rubidium atoms. They have internal Zeeman structure and hyperfine structure. They act a little bit like magnets. And these magnets are not very good for time reciprocity. And so what I showed you before was actually this small peak here on rubidium. So it was only 1.1 high. To recover the full strength of the interference I mentioned in the first slide, you need to go for a transition which has no Zeeman substructure in the ground state. So we did the experiment this time here with strontium, and you can recover the full interference effect. But it's a little bit more difficult to do with strontium than rubidium. This is why so far very few people have done this experiment with atoms other than rubidium. But this could be a fundamental problem, and we are working along this line to solve this type of problem. Okay, so far we have seen weak corrections. Now we want to go for strong corrections. And when we wanted to push this further, we became aware about the problems of this universal theory of localization. So for this, we developed a new model for light scattering, not really new model, but we pushed harder a model to explain all our experiments and to see if localization can be possible. And the model is sketched here. So instead of taking just approximate model for the mean free path, we take an atomic physics model. So that's why we like cold atoms, because we can do ab initio models from Hamiltonians. Then we trace over the degrees of freedom we don't measure. So that's what we in our community do all the time. But people in condensed matter don't do so often. So we take here all our atoms, which are our resonant two-level systems, and then we have our dynamic equations, which can be derived from optical block equations. So this is the driving term with the rubber frequency of the instant electric field. And then there's a phase of the electric field, which depends on the position of the atom. And then we have the free evolution of this optical coherence here, which decays with gamma over 2 and has this detuning oscillation term. And then we have the other term here, which is the collective term, which is the field hitting atom J, but which has been scattered by atom M. So there's an electric field which first goes to atom M, and then it scatters to J, and then it drives the atom J. And so it depends on the amplitude of this amplitude of the dipole M, and then there's a Green function which describes the propagation from atom M to J. It's a simplified model, but okay, this is basically the idea. From this, I can solve this equation, and then I will know all the dipoles, and if I know all the dipoles, I can compute the field which is coming out of my system, which I detect. So what's important to know is that this is 1 over R term in the Green function, which corresponds to long-range interactions, a little bit like gravitational physics or Coulomb interactions. And this is very different in scaling laws from what you expect in other type of near-field interaction physics. So we come to this maybe at some point, but it's very important that this is 1 over R term. So we take our model and then we solve it. So what can we see? If you come in with the plane wave here on the cloud of cold atoms, in orange here, I look at the scattered field. I see this speckle field here. In the forward direction, I see a very strong peak here. So if I plot an azimuthal average about this detected far field emission diagram, I get the blue line for my model. In this blue line, I see first a very strong peak here. That's the most prominent feature here. And this is actually just something I would get by replacing this cloud of cold atoms by a dielectric bead, by C of glass with the same dielectric constant. So this is like a mean field response of my cloud of cold atoms, and this acts like a lens. So that's basically a lensing effect here. It's very strong. And this has been measured by Junji in the experiment recently, because you need to look straight in the laser beam, which is a little bit difficult to do technically, but he succeeded to do this. Then, if you look in the other direction, if you do the averaging of the speckle field, you get a curved line here, which is actually hidden behind this black point. And these black points come from a random walk model, so no interference effect. So this model I showed in the previous slide includes the mean field. It includes also random walk model. But the most interesting thing is it also includes this current backscattering peak here, which is not included neither in the mean field nor in the random walk model. So this microscopic ab initio model includes all features known so far from light scattering by resonant systems. So that's why we like this model very much. And we think this model can lead us to into the Anders localization regime. So this was steady state predictions. We can also do time-dependent predictions. And to understand this time-dependent prediction from this coupled dipole model, this brings us to the kind of Decay type of cooperative scattering. So Decay studied what happens if you have many atoms and you have a lot of excitation. So the most known famous result is that if you start from a fully inverted system, then you will decay along this symmetric state and light will come out in a pulse regime much faster than if you would have a single atom. So this is called super radiant, Decay Super Radians from a fully inverted system. And this has been observed by Felt in the 70s. So this is well known. But that's not actually what we do. We want to look at what happens if you don't start from a fully inverted system, but you go into the linear optics regime where you only have one photon coming in. And then you have to go for the single photon excitation, low intensity limit, and then you still have a super radiant and the sub radiant manifold. So one super radiant state which decays faster than a single atom, and all the other states which don't decay very quickly, which I call sub radiant states. On top of this, we have to adapt the model for large volume because we don't have a volume which is much smaller than the wavelength, which has been the main focus of Decay's paper. So in that case, this n enhancement factor will be replaced by another number, and this number is the equivalent of the cooperativity factor we know from atomic physics in cavities. So if you have atomic physics in cavities, in a cavity you have a single mode, and then you get enhancement factor by how many atoms you have in this mode. This is n at here. But now in our system, we don't have mirrors. So we have to count the number of optical modes which are available in our system. So if you consider a room, a box, the number of optical modes which can leave this system goes like the surface of the system divided by lambda squared. So L, the typical size of the system divided by lambda squared, this is the number of optical modes you have. So the cooperativity parameter now is how many atoms you have divided by how many optical modes are available. And so this is what I call B0 here. So this is a kind of a generalized cooperativity parameter. It is also the on-resonant optical depth of our system. So we like it very much, this number here, because it's the scaling parameter for the physics we want to study. And it's also something we can easily measure and calibrate in the experiment. Okay, so based on this, we did some numeric simulation using our coupled dipole model. And we come in with the pulse, and we see that if you have many atoms, instead of having this single atom exponential decay, we get a fast decay and a slow decay, so what we call super radiant and sub radiant. And we looked how this scales. So it scales like the optical thickness. So this was numeric prediction in 2012. Sounds easy, but the experiment was very difficult to do because you get very slow, very little light in this sub radiant state. So the main challenge here for many years was how to switch off the laser by many orders of magnitude. So when you switch off the laser, you want to have it zero afterwards. You want to switch it off, and you have to switch it off in a few nanoseconds or tens of nanoseconds. So that's not so easy, but at the end we succeeded in doing this. And here is the result. So if you switch off the laser, there's a fast decay here, which I don't focus on now, and then we have slow decay here. And if we increase the optical depth of our system, we see that the slope here gets smaller and smaller. And if we change the tuning of our laser, we get more or less light coming out in this slow decay mode, but the slope is not changing. So if you take all this data together, we could scale it on a single scaling parameter, and the lifetime of this slow decaying mode was increasing linearly with this cooperativity parameter introduced before. And so this is exactly what you expect from Decay Sub Radians. And what you can see is that you get a 2 orders of magnitude increasement in the lifetime. So it's not just a small correction, it's a big correction. So this is a result we got now 5 years ago. And since then we studied many details on this, but I will skip the details. But this was like a big, this paper has a big impact because it opened the door to a lot of cooperative scattering physics with cold atoms. Now, again, so we want to go for Anders localization. So we took our model and now we put it into a more Hamiltonian approach and try to look at eigenstates. And if you look at the eigenstates, so this is would be the effective Hamiltonian of the system. So it's an open system, light can escape. So there are eyes here, so that it's an open quantum system here. So this would be the single on-site Hamiltonian. That's an energy of the resonance of the atom. That's a decay, the light can go away of this population of the excited state. And then there's a coupling term between different atoms or different sides of this system. And the coupling term here, which is the green function in our system, also is a complex number. So there are eyes around here. And if you look in detail, this coupling term here has the long-range term here, 1 over r, which I showed before, and also things I didn't show before because I tried to go quickly. There are near-field terms here, 1 over r cubed. This is typically the near-field dipole-dipole coupling term, which you have to take into account if you want to do this precisely. So this is very reminiscent of an Anderson model. So there's an on-site Hamiltonian and there's a hoping term here. And now we can play with this to see if we can see Anders localization. The most important difference is that it's an open quantum system, the eyes here and here, and it has long-range terms. So this makes it very different from the Anderson model, which has been studied for electrons typically. So we want to look if there are eigenstates, if they're localized. So you can picture this cloud of cold atoms actually like a big molecule, and you want to find the eigenstate of this molecule. So if this cloud would be dilute, the spectrum of this eigenstate would be very similar to a single atom spectrum, so Lorentzian peak here. But if these atoms are very close together, like in a big dense molecule, you get a lot of lines here. So you get all these molecular lines. And some of the lines are broad and some are very narrow. And these narrow lines corresponds to these localized states. That's what we're looking for. So this type of narrow lines have been studied in different communities, and every community has different name for this. It goes with different names, but it's the same type of physics of a coupled resonator system. So it's an antenna theory, basically. So our question is, from this type of result, can we see if there's an Anderson localization transition in 3D for light? And so we studied this in detail, and so we followed up on this scaling universal scaling paper, which I mentioned by the Gang of Four. That's why I mentioned this paper. So this paper says that if you compute the right scaling function, which I won't have time to enter in detail, this scaling function should cross 0 if you get the phase transition in 3D. And in 1 and 2D, it will not cross 0, so there's no phase transition in 1 and 2D. And in 3D, you get a phase transition. One crucial parameter to consider in this scaling function is the so-called Powerless conductivity, which is basically the idea is given by how far are different eigenvalues and compared to the width of this eigenvalue. So the distance, the average distance between this mode compared to the average width of this mode. This tells you if these modes are isolated, so you get localization, or if they're overlapping, and then you would get transport. So what we did is we compared this scaling function here for different cases. One where we take just the long-range term 1 over r, which was the one I showed in the first time I showed you the model, and one with the full green function with the near-field term. And what you can see is that this scaling function beta here, for the scalar case, it crosses 0, so there's a phase transition. But if you take the vectorial case, which is the case when you take into account the near-field terms and the polarization of the light, then this term does not cross 0. So real photons in our system are not scalar photons, they have polarization. So for real photons, from this model, there is no phase transition for Anders localization. So this has been a big blow for our community, for at least people who look into this in detail. And Sergei Skipetrov did this shortly before us, but he did this first. And so this says that in 3D at this stage, there is no Anders localization of light for resonant cold atoms or 0 to 1 dipole transition. So this means no one has seen it because it doesn't exist. And so another important issue is that this big difference between the different models of the green function has not been captured by the universal scaling theory, which basically the idea was that microscopic details are not important. Here we see that the microscopic details of the green function make a complete qualitative difference of the existence or not of the phase position. So this is why this is very important and a game changer in our community. So that will be very bad news. But of course, once you understand what's happening, then you try to find solutions. And right now there are two solutions on the market. One which has been suggested by Sergei Skibitrov and Igor Sokolov, which is to apply a strong magnetic field, and then you can recover at some frequencies under localization. Again, this is very strange because you add a strong magnetic field, which is something typically you don't want to do to have time reversal symmetry, but it works. So that's one possibility, and the other possibility is to add diagonal disorder, as in the Anderson model, not only having random hopping terms, but also random on-site energy terms. And that's something we studied together with Luca Celato, and there also we see a localized term. So these are proposals, and this is where we want to go now in future. So that's our experiment with the ongoing ERC project, which Tabato mentioned in the beginning. This is what we want to do, explore these two different roads to see if you can see under localization. Other people have high density samples, like in Antoine Breuer's group. In Munich, they have seen separated mirrors by having order included. And so now of course, everyone is looking how to make quantum memories out of this, or see entanglement in this. So if you have new ideas on this, please contact us. We'll be very happy to explore new things. So that's how far I went with under localization. It's more time than I thought, of course. But now I will spend a little bit time on another topic, which happens if you have some photons and a lot of atoms, which is Levy Flight of photons. And actually, I don't have time to tell you how we came on this, but it's also when we wanted to study in detail corrections to the diffusion coefficient, that is found that there would be corrections which at the end led us to the Levy Flight studies. Okay, so what is Levy Flight? So first, in a regular random walk, Brownian motion, you would have a photon or particle which makes a Brownian motion, which is described by diffusion coefficient. So this is a typical trajectory here, which has some small steps, big steps. And if you look at the step size distribution P of x, if you take the average of x with this distribution function, you normalize it properly, then you get what is called the scattering mean free path. And if you take the average of the square of x with this diffusion function, you get the diffusion coefficient. And if you take an exponential step size distribution, which is what you have if you throw a laser beam in a glass of milk, then you get a mean free path. So this value here is finite, and we call it the mean free path. And even the average squared is finite, and we call it the diffusion coefficient. So all this is well behaved if the mean free path and the average of the square here are finite and exist. But this is not always the case. If you have a step size distribution which decays not as fast as an exponential, but with at the power law here, x to the mu, and depending on mu, if mu is smaller than 3, then the average of x squared is already diverging, it's infinite. So you can no longer define a diffusion coefficient. If mu is even smaller than 2, even the mean free path diverges. So the question is, can we find this type of very strange step size distributions in our atomic physics experiments, and how to probe this? And again, nothing new. This has been studied for many, many decades. And this is actually the study of multiple scattering of light in hot atomic vapors, which exist in discharge lamps, in stars, in many systems. And so if you would take a diffusion equation to describe this, for instance, if you want to know how long would it take a photon which would be created at the center of the sun to leave the sun and then come to us in a few minutes. If you would take a diffusion equation, you will get the completely wrong answer. And the right answer is given by this Holstein equation here, where we see that the very important ingredient is, again, this green function. It's how far a photon goes between position R and M R prime. So this is the microscopic ingredient in the proper description of light propagation in hot sapphires. So this has been studied by Canty in 32, so very old study, and he worked for the General Electric Vapor Lamp Company. So you see, it was already applied physics, but and he already said that if you have a system where you have lots of Doppler broadening, then the diffusion coefficient, the average square mean free path, and even maybe the average free mean path might become infinite. So you will no longer have a diffusion equation to solve this. So the question is, can we measure this green function, which I mentioned before, in the lab? So it's very difficult to track a photon in the sun. So if you would have a radioactive particle, you could label it and then you could make a tracer particle. But how to make radioactive photons? It's very difficult to do. So we came up with a trick. So of course we cheated always. A trick is always going around difficulties to measure this green function here. So how we did this is shown here. We come in with a laser beam on the first cell of rubidium atom. Then the photons which will scatter here will be Doppler bound. They get Doppler shifted. So this is a monochromatic frequency here. But photons going out of this cell will have all the Doppler broadening already. And then we collimate this with two diaphragms here. And then we go on an observation cell, which has a very dilute density of rubidium. So there will be no multiple scattering involved here. So some of these photons here will be scattered at the entrance of the cell and go to the camera and make a picture of this. And some photons go to the end of the cell, much less, and we make a picture. So by looking at how far the photons go in this observation cell, we can measure the path length distribution in this observation cell here. Okay, so if you do this, if you would come in with a laser beam directly on this observation cell, you would see this Lambert's law, which on the log-log scale looks like this curved slope here. So that's an exponential. But if you go for this rescattered photon, where we have the Doppler broadening of the photons, we get a power law here. And the slope we get here is 2.2. So it's well below 3. So this qualifies for this Levy Flight, because in this case, if the coefficient is below 3, the average of the x squared will be infinite. So there's no diffusion coefficient any longer in this system. So this is one way to do it. This was very difficult to do, very hard experiment. Later on, we came up with an easier way to detect this by looking at spatial profiles and the total diffuse transmission. So we take a cell of rubidium here, which is in a kind of a camembert geometry. So in 2D BC, sometimes we call it something pancake geometry. It's very thin, but we need some propagation distance, so it's still larger than thick. So we call this a camembert because we're from France. So then we look at the light going through, and we look at the distribution where the light goes through, and with the camera, and we look at how many light goes through by the integration on the camera here. If you do this, you find that if you look at the total transmitted light, it decays like 1 over L times alpha over 2. If alpha would be, if it would be Ohm's law for photons, alpha should be equal to 2. Then it would be like 1 over L. But anything decaying slower than this, so if alpha is smaller than 2, so mu is smaller than 3, you get deviation from the diffusive law. And what you get from this experimental data here, you extract a coefficient which is close to 1. So again, it's well below the regime where you expect a diffusion model to be possible. You can also look at the spatial profile of this and make a fit in the ring. And the prediction is that it goes like 1 to the r power 3 plus alpha. And again, we get an alpha close to 1. So we now have 3 different ways how to extract the Levy coefficient. One, the hard way, which is this tracer, photon tracer model, and then much easier ways by looking at spatial profiles and total transmission. And here we see that all this is consistent with a diverging diffusion coefficient for the Levy exponent. Now we wanted to see if you can push this even further and if you can enter the regime where even the mean free path is diverging. And for this, we need to control this coefficient here. And we can do this because from atomic physics, again, we know that the spectrum of the scattered photon and the scattering cross-section for the reabsorption of the next photon can be changed very drastically by collisional broadening. So by adding in our cell a buffer gas, which here was a buffer gas of helium, we can completely change the optical block equations of the system to be described, so the scattering properties, and we get collisionally broadened lines which have Lorentz shapes and no Gaussian shapes. And then doing the similar experiments by looking at the total diffuse transmission and the spatial profile, which with a different cell here. Don't go into details, but here we extract a coefficient alpha of close to 1/2. So alpha being close to 1/2 means that the coefficient mu is below 2. So this is a signature of a situation where even the mean free path is diverging. So by adding more or less buffer gas, you can control this Levy exponent, and so you can control the way photons propagate in this system. Okay, so there's much more to do. In particular, you want to do for time-dependent experiments here to go for Levy walks, but okay, there's still a lot of things to be done. And these systems here are based on hot vapors, so the cost of these experiments is much less than ultra-cold gases experiment and so on. But you need to be clever and find new ways how to design experiments to extract new results. Okay, so so far so good. I think I have time to come to the last topic I wanted to cover in this talk, which is about intensity correlation. And this brings me from our cold atom experiment to hot vapors to astrophysics. So it's really reaching many orders of magnitudes in system sizes and samples. Okay, so let's start first from the astrophysical perspective. So astrophysicists, they always wanted to look at planets and stars, and one thing they wanted to do, have a good resolution. So you take a microscope, a telescope, and the larger your telescope, the better resolution you get. And so this is called interferometric images, and there have been nice tricks pioneered by Michelson many years ago, and then pushed really hard by Antoine Labeyrie, the father of Guillaume Labeyrie, here in Calais next to our lab, and which has been the forefront of what is now called the VLTI in Chile, and the Chara consortium and now on Wilson. So these are microscopes where the diameter of your lens is typically a few hundred meters large. So, but even though that this diameter is very large, the numerical aperture is very small because the objects are very far away. So the resolution is still limited, but that's the best microscope for stars we have so far today. So the idea is, can we do better than this? Actually, there has been a technique which has been proposed before the development of this interferometric system, which is due to Henry Brown and Twiss. And they looked at two detectors. They did not make the interference between these two detectors because that was much too hard to do. But they look at intensity correlations between these two detectors, which was very hard, but still possible. And so they first studied this type of things in the lab, and then UK, and then they built this platform here in Australia. And they have two telescopes which they could place on the rail here, and they could get very large separation. And they could, by this separation here, you get the same resolution as in a microscope without having the interference of the two parts. So you don't need to stabilize these two telescopes at the wavelength precision, which you need to do if you want to make fringes. So if you want to make a Michelson interferometer, these two parts need to be stabilized at the lambda precision, which is too difficult. With this technique, you can do it without this high precision stabilization of the telescope. So Henry Brown and Twiss, they measured the angular diameters of 32 bright stars in the 70s, and then actually they stopped this because this technique here of the VLTI was developed, and they thought this is much better, and indeed it has a much better signal to noise ratio. It's much more sensitive. That's why this technique has been stopped. But we think there's still room to improve now the numerical aperture of this microscope for stars by coming back to this technique. And so we took up this technique. So the challenge is that you need to have intensity correlation with a very high bandwidth, which was very difficult to do in the 80s and 70s. But now with all these quantum optics experiments we have from cold atoms and quantum optics, there's no detectors around. And so we studied this. So we took the setup which we developed for Levy Flight, for hot vapors here, and we look at light which is scattered from these hot vapors close to forward direction here. and we make an 100-bounded twist experiment. So we look at intensity correlation after a fiber splitter here, and we saw bunching of photons because photons are bosons, so they want to stay together as predicted. The novelty here is that now we have a nanosecond, sub-nanosecond resolution. Actually, we have now a few hundred picoseconds, so 300 picosecond time resolution, which is much better than what 100-bounded twist had in the 60s. So these experiments here have been tested in the lab on hot vapors on thermal lamps. When we took this setup to cold atoms, that was easy cake. So this was very easy because in cold atom timescales are microseconds. So everything which was hard to prepare for astrophysics was in this case very easy for cold atoms. But we need to get these fast detectors under control. Okay, so then we did experiments at the same site where this interferometry technique has been developed by the father of Guillaume. We took our system, we put it on the telescope with some appropriate splitting techniques, and we looked at 3 different stars, and we were able from light from the stars again to see bunching of light as expected. There was a lot of technical challenges, but basically this here has been the first bunching signal of starlight since 100-bounded twist, and it's the first one which has been done in the photon counting regime, which was not the case 100-bounded twist were doing. So we are in the photon, we count every photon, and we are short noise limited in this technique. Okay, then we did experiments, of course, with 2 telescopes with a microscope for stars, and we did this on different stars here, so this worked very well. Then we also did this now on emission lines, because we have fast detectors and we have narrow filters. We can look at very narrow emission lines, which has been the first application of our technique, because we could do this on supergiant stars. There are some stars who have very strange behavior. They want to explode almost, and they get very strong emission lines. And comparing our bunching experiments to state-of-the-art astrophysical modeling, we have a new alternative distance calibration of this supergiant stars, which could, if this extends to other stars, be a new calibration for the size of the universe in a regime where the Cepheids are not appropriate. So we already go for applications of our system, not really for resolution, but for distance calibration. And then, of course, the goal is to implement our systems on the best telescopes, because our telescopes here have only 1 meter diameter. We want to get more signals, so we want to go for the big telescopes. So we have to show that our system is transportable. So in 2019, together with cooperation of our Brazilian colleagues, we were able to access the SOA telescope in Chile. And even though it was very bad night, you can see here there's a lot of clouds, there was a lot of wind, there was full moon. You can see the shadow here. So it's a situation where astrophysics people, they just don't observe. Despite this difficulty, we could see bunching of photons and our system and prove that we can easily transfer it from our lab to a more hostile environment. And after this, we got approved now to test our system on the VLT. This should be a VLT, and this will be called the VLT-QI for quantum interferometry. This works. So we have been scheduled last year. It has been proposed because of the pandemic. Now we send our equipment already there. It's already installed in some of these AT testing telescopes. And if this works, then afterwards we want to go for the big telescope to extend this intensity correlation on the state-of-the-art telescope in the world. Of course, we are now, so this technique sounds nice, and we are not the only one doing this. There are other people working on this. In particular, there are people who work on what is called a Cherenkov telescope array, which have huge telescopes. So they have 20-meter telescopes, so they have much larger area. But these telescopes are poor optical quality, but it still can work for photon bunching. And they have recently, last year and this year, published papers, but they also now can study this photon bunching. They see this photon bunching effect. They cannot go for narrow lines because the optical quality is not good enough for these narrow filters. But this is a very promising technique to exploit systems which exist for intensity correlation. And also there's a group in Italy who has now seen photon bunching with the same technique, very similar technique what we have in Italy. So there are more and more groups joining this photon bunching effect. And my personal goal is not really to build a big microscope, but I want to look for signatures of quantum optics in space, because basically what we have in space is a lot of hydrogen atoms, so it's a lot of atomic physics actually. So this is where we are experts. So I would, for instance, want to see signatures of random lasing in space. So we did some experiment on random lasing in the lab already, and it has been shown that photon bunching could be a good signature if you have the transition to lasing regime in space. And there have been predictions that eta Carinae would be a good start to do this. So this is actually my motivation. I want to look for quantum optics in space. I know if squeezing can be done. So this would open new eye on the cosmos by looking at quantum optics instead of looking only at intensity and spectra and color of the light coming, on top, of course, of the neutrino and the gravitational waves we already have now. Okay, and with this, I just want to say that my connection with Brazil is very diverse. I have a lot of work with, I could not mention here, I have collaboration with Vanderlei Banhato in San Carlos about matter wave speckle and turbulence. We want to see if we can use light scattering to study turbulence in his BCs. With the Philippe Cortez group and Raul Teixeira's group, we have been looking at current backscattering with the mirror, helping this effect to be seen in their cold atom experiment. We have done intensity correlation experiment with random fiber lasers with Anderson Gomez when he came here to Nice, and with Tommaso Matri we have now a project on quantum fluids of light and multi-level atoms. And with this, it's time to stop, and I thank you for your attention. And just in case you want to come to Nice, we have open position, PhD, postdoc, so contact me and we'll see what we can do. Thank you for your attention, and I don't know now, Tommaso, how to handle if there are questions. I'll let this up to you. Thank you.
Thank you very much, Robin. You can hear me, right?
Yes.
Okay, great. So thank you for the very beautiful talk. I really enjoyed, and I hope that also our viewers in YouTube enjoyed it. I think that we have some questions from YouTube. So the first one, when talking about the problems to face, you mentioned that higher densities would be desirable. I think this question has to do with the first part on undersea localization. Can you briefly comment on that, Raban?
So following the universal theory of localization, you want to have the Regel criterion fulfilled, which is KL of order of 1. We don't know if it's 1 or 2 or 0.5, but of the order of 1, which means that the scattering mean free path needs to be of the order of lambda over 2 pi, which is very small, which means that you need at least an atom at this distance, else you cannot scatter. And this corresponds to atomic densities of the order of 10 to the 14th atoms per cc. So this is typical densities which you can have in dipole traps or in BCs. But it's difficult to do this without having other spurious effects like light-assisted collision. So you might have losses. And typically when you get these high density samples, you get it with less than 10 to the 7 atoms, you get less signal. But we're going to see how it can be done. So if someone has, and I know some people trying this, have large samples of atoms with above 10 to the 13, let's say 10 to the 14th atom per cc, that's something to go for. And ideally, you want to have something where you don't have a degenerate ground state. So rubidium or all the alkali BCs are probably not the way to go, because all these Raman transitions between the Zeeman sublevels or hyperfine levels are probably not good to keep the coherence of this Anderson localized state. So strontium, ytterbium, calcium, magnesium, or any 0-1 transition at these densities, and you can then the next one, if you have these densities, you have to be careful that you don't destroy the sample when you probe it. Okay, and then the question is, what would be the right appropriate signature that you have localization? So this violation of Ohm's law might be one thing, but it might not be the best way to do it. It's not sure that there will be no other consequences of this long-range dipole-dipole interaction. So we are still hunting, so the community is still hunting for the best signature to observe under localization. We have learned from the community what can go wrong from the people who did semiconductor powders or white paint. So we know a lot of problems. So we have to first address these problems and make sure that this is solved. And then we have to typically come from our Hamiltonian ab initio approach and see if we can model what we can detect.
Okay, thank you, Roman. Maybe a related question from Heitor. So could you please comment on the possibility of studying undersea localization in other experimental platforms that provide either higher densities, for example, hot vapors. You were talking about this in the second part of the talk, and how other effects such as Doppler broadening and others could affect in a good way or bad way the localization problem.
Unfortunately, I think it's a bad way, but so that's how actually we came to the Levy Flight. So when we look at this benchmarking experiment, how long photons stay in the sample, actually we saw that photons escape our cold atom cloud a little bit faster than what we expected from a system where the atoms would not move. And even laser-cooled atoms, they move a little bit, and this destroys the coherent backscattering effect and the transport. And it's very small correction, but when you go for hot vapors, this Doppler shift is very important and becomes dominant, and you get Levy Flight. So so for now, we think that this will destroy localization. We have not even seen yet coherent backscattering, so weak localization from hot vapors. We are working on this. We have a paper now just out on the theory, how to detect it. We have tried to see it. We have not seen it. It might be much reduced. So it's probably not a good way to get already reduced weak localization if you want to go for strong localization. And the picture you can have in mind is that if you want to get an underlocalized mode, so you have in this eigenstate, you have a few atoms, and the photons, they are shared between these few atoms. But it will take some time for these photons to share between these atoms. Let's say you have 10 atoms which share an underlocalized mode. So you make hoping between 10 atoms. This takes some time because typically a scattering event takes gamma -1. So it takes time. If during this time scale, one atom has moved the position by more than lambda, then this interference will be destroyed. So hot vapors, they move so quickly that probably you cannot make a kind of a stable mode fast enough. And so that's why I think underlocalization in hot vapors will be extremely difficult to achieve.
I see. Oh, Bam, maybe I have a curiosity related to this problem. You were proposing as a sort of theoretical model to understand whether there is or there is not localization in now back to cold atoms. These long range sort of XY model, so this OPIM model plus a local term, right? And you were commenting that the local or the specific details of the green function might have actually indeed affect the behavior of the beta function for the localization transition. And actually my curiosity is related to whether it is the long range part or it is the dissipative nature of the green function that actually gives rise to this behavior. Do you have an answer?
It's a long range part. So actually it's let me come back to just show you what's happening. So can you see my
Yes, I can see it.
So so this is the full green function if you take into account a 0 to 1 transition, which is the best we can do so far for the atomic physics part, which would be the case for strontium or ytterbium atoms. And this is the green function, which has a real part and an imaginary part. So if you replace this green function here, this green function here has no localization if you don't apply a strong magnetic field.
Okay.
So it has, because it has this 1 over r cubed term here. The other green function, which is shown here, this presents localization. So it's exactly very precisely. So it's here. This term here has not doesn't have exact. So if you cancel these terms here, the 1 over cube and 1 over r squared, you still have these p factors here, which has an anisotropy of the radiation for. So, but if you put this in isotropic way, then you get if you can get rid of these near field terms, then you get the localization. So the scalar model is a kind of an isotropic long-range term. This has localization, and the other one has no localization, which is really counterintuitive because you would think from the Anderson model that long range would kill. But this is a kind of a correlation in the long-range hoping. It's not a random long-range hoping. So the random matrix you construct is not a random matrix you typically construct in the Anderson model where you just for random numbers at every point in the matrix. So it's a Hermitian matrix. So it's a symmetric matrix, which makes it a very different situation.
Ruban, maybe a related question. We have another question from YouTube, but since we are at this slide, and you were commenting on the universality properties of the beta function, of course, that is related to universality in statistical physics, I guess. And since here you don't observe localization, can you comment, I mean, if you take into account the full model, can you comment on the universality of this model in terms of other simplified statistical physics model that you might be aware of?
Yeah. So no, okay. I say the full answer is no. I don't know, but there's some things where to go. So this looks very similar to a spin orbit coupling. So there are some classes of localization where you don't have where you break some symmetries, and so this is in same context. Let's say how to study universality if you have some symmetry breaking argument. Then the other thing, so we studied this also in lower dimensions, but it basically reproduces what you see in 3D. For instance, what you would expect in 2D here from the universal scaling field, that you always have localization. But what we have seen together with Romain Bachelard, that in 2D, if you take the full green function for 2D scattering event, you have no localization. So it's even 2D, it's not only the phase transition in 3D which goes away with this exact green function, but even the localization in 2D goes away if you take the full green function. But in 2D you can control the polarization. In 3D you cannot control the polarization. But in 2D you can control it, and in 2D, if you control the polarization to stay always perpendicular to the scattering direction, you have localization, but it's in plane, then you lose the localization. So even 2D, where people thought there's no open issue, this localization ansatz has this theory has not captured this feature.
I see. Okay. Roman, then another question from Andre. Great talk, Roman. One quick question. What are the quantum effects you expect to see from eta Carinae, a binary system that you were mentioning as at the end of the talk?
Eta Carinae, there has been a lot of effort by Letokov. Actually, Letokov is one of my heroes. So Letokov studied random lasing. He was doing cold atoms, and he did also astrophysics. And so he studied this is probably the book I showed over here. So Letokov and Johnson, they studied a whole range of stars where you could combine population inversion and rescattering. So you get random lasing, you need gain and scattering. And so not all stars have this feature. And to get inversion of population, you need a very bright source which pumps your atom via the ionization state, and then it drains down all the excited states level. But then if you have one transition where you have scattering, you need to rescatter this photon. So you need the right situation where you have some iron atoms, in this case, in an outer layer where this light can be rescattered and it's pumped from the core. So this is, I would say, it's quantum optics in the sense that the photon bunching would disappear. So this is what you expect for laser physics. So it's a signature of spontaneous creation of coherence in space. Okay, so it's a generation of time coherence. I don't know. I think no one has really studied if you could get other type of non-classical optics in this system, like squeezing or non-classical fluctuations. So we have been studying together with Luis Orozco if there are other measures of detecting non-classical fluctuations, and there's something called intensity field correlations. So not intensity correlations, and not field correlations, which would be interference effect, but intensity field correlations, and they would be very sensitive to squeezing effects. But so far, I don't know of any astrophysical source which is predicted to have this feature included. But okay, no one has looked at it so far. So yeah, so that's my quantum optics part. So there are a couple of, actually there are many lasers which are known and masers which are known. So population inversion and gain is well known. For instance, we know that the CO2 line at 10 micron in Mars has gain, but it's single pass gain. There's no rescattering. So you have gain. And sometimes people in astrophysics community call gain, so amplified spontaneous emission, they call this lasing. But okay, for me, lasing is when you have a spontaneous generation of coherence, which is not the case in amplified spontaneous emission. But if you saturate the amplified spontaneous emission, then you get a flattened G2, and that's where you have, well, for me, the spontaneous creation of coherence.
Okay, thank you, Robin. I would like to, okay, since there are no other questions, I have actually a curiosity regarding the Levy Flight part, the second part of the talk, since nobody asked. I mean, I'm not of course, I'm not an expert, and I don't know much about Levy flights, but I know that they are very well applied in other fields, such as econophysics or in ecology for these predator-prey models. I wanted to, this is just a sort of speculation. We talk a lot nowadays about quantum simulation, so to use experimental platforms to understand other models. From, I don't know, statistical physics, quantum mechanics, etc. Do you think that your experimental setups might be useful to understand a little bit more about other physical systems?
Let me see where I have something. No, I had to throw the slides out. Of course, so Levy flights have been studied in very different communities. Some papers, the most famous papers actually, the authors themselves said that it was not Levy flights, like albatrosses or following money, travel of the banknotes. So some things are not Levy flights, but okay, it's detailed. Basically, there are a lot of Levy flights in different systems, and one thing which is very different, let me see that, which is very different in different systems, is that you have to distinguish annealed disorder and quench disorder. For instance, if you take a piece of glass, this has been done by Diederik Wiersma, he takes some beads and he assembles them properly so that the step size distribution is no longer random, but it has some bigger steps and smaller steps with the right distribution, and you can reproduce Levy flight. But if a photon goes to the same position, it will do the same distance. So that's a correlated random walk. In our case, we have no correlation, so we have annealed disorder. So now if you want to use this system to simulate something, for instance, you want to anticipate a financial crash, okay? So you get enhanced fluctuation at phase transitions. Actually, just before the phase transition, you get Levy statistics, okay? So can you look at different statistical properties before a crash? So then the question is, what type of disorder you have in the crash? So just one example, okay? So if you can mimic the correlations and the disorder you have in the crash, you can make predictions probably. I agree, you could do this type of thing. But I discussed this with a mathematician on financial studies, because a lot of people who do a lot of statistical physics, like Simon, he created a renaissance in the US. One of the biggest funds in the US is coming from a mathematician who created a company. In France, we have Bouchot, who created a company. He comes from Levy flight. So if you know a lot of statistical physics, you'll be hired immediately by the finance market. But the question is, if you suppose you can predict this very well, what would you do? You would regulate this to avoid the crash. Of course, you don't want the crash. And this means you would push the relation so far that you avoid the crash. It's like earthquake. But at some point, you make a default, and then the crash will even be more dramatic. So I'm not sure if it's a good way to make a feedback on the real system. You can exploit it maybe, and people do it. So this is done. People do this studies, and they do it with computers, heavy computing. So the question now is, so this is done. That's what people do in the stock market all the time. They don't have Gaussian statistics. Well beyond this. The question is, how fast are you? So, because people now they go a millisecond timescales to buy and sell things. So if you can do this faster than the computer, maybe, but you need to feed the system with a lot of information. So I don't know how to do this yet. But the computing time here is much faster than typical real-time computer. We exploit this for another system, but so it's you need to fit in the system. Maybe you can do faster computation, and then you have something to do.
Thank you, Robin. We have maybe the last question from YouTube, from Tabosa, from Recife. Thank you for the talk. Concerning the random laser in cold atoms via population inversion. I was wondering if it is possible to observe random lasing without a population inversion.
Oh, okay. Typically, I would say no. You need inversion to have gain, but of course, Tabosa asked the question, so he's an expert. So of course, there's lasing without inversion with some very specific system. Okay, I didn't look into this, but I don't see a fundamental reason why not to have the same mechanism as has been studied in lasing without inversion in a random lasing medium. We didn't study it, but I don't see a fundamental objection because you need incoherent pumping for the lasing without inversion. And so I don't see a fundamental reason why this should not be possible, but I've never looked into detail how to do it. But okay, yeah, so it would be a nice thing to do.
Okay, then, Robin, thank you very much for the talk. I think that we had a very nice interaction also at the end with the participants. I would like
Thanks for the whole community. I'm very happy to interact with Brazil.
Yeah, thanks a lot to all the viewers. Of course, the talk will be available on YouTube. So if any of you lost some parts of that, please go on our YouTube page and you can still watch it in full. And with this, I would like to thank again Robin for being with us today. And the next colloquium will be in August. Thank you very much, everyone. Bye-bye.